We often associate intelligence with the sheer physical scale of the hardware. We build massive data centers that stretch across miles, assuming that more servers and more power automatically equal more thought. But storing trillions of data points is a feat of engineering, not necessarily one of learning. It is a brute force approach to memory. To find the actual mechanism of learning, we have to look past the scale and start with the way a standard, non-intelligent computer operates. This is a standard calculation. You start with inputs A and B, applying a fixed rule M. The result, R, is the inevitable outcome. When provided the rule, the machine simply executes it. The path is paved, and the outcome is perfectly predictable. This system can run the same equation a billion times, but it will never understand why the math works. It can execute, but it cannot discover. Learning begins when we remove that paved path. What happens when the machine has the data but no instructions on what to do with it? This is where the flow of logic reverses. We still have the inputs, A and B, and we have the final result, R. But the rule, M, is now a hidden variable. The system is no longer calculating a result. It is testing different operators to find the specific structural law that connects the inputs to the output. This is the primary objective of a neural network, working backward from observation to identify the hidden logic that governs a system. Solving for that single hidden rule doesn't require massive complexity or billions of parameters. At its core, it is a search for an identity. This inversion, moving from the execution of a rule to the discovery of one, is the defining shift that turns a calculator into a learner. To understand this process, we have to look at how a system handles uncertainty. This scatterplot shows a system with almost no information. We have a single data point, but an infinite number of possible rules could pass through it. At this stage, the machine can only guess. As soon as a second point of data appears, the symmetry breaks, the noise vanishes, and the system is left with a single trajectory that fits both pieces of evidence. This is the system finding a point of stability. It is no longer drifting between infinite possibilities. It has found the most efficient path that explains the data. This is not a lucky guess. It's a structural elimination of every rule that doesn't fit the facts. We can define the moment learning occurs as this specific transition, where uncertainty collapses and a mathematical truth becomes visible. When we look at the largest AI models today, they often move away from this exactness. Instead of finding the specific rule, massive networks often use brute force to approximate a solution, layering millions of weights to mimic a pattern they haven't quite decoded. This chaotic web represents that approach, trying to approximate a curve rather than identifying the precise geometric operator that creates harmony. A more efficient system doesn't need more weights. It finds the balance where the rule matches reality. Learning, in this sense, is the act of stripping away the computational noise until the only thing left is the law that governs the system. Whether it's a computer model or a human researcher, the goal is the same: to look at the surface of the world and deduce the hidden mechanics that make it work. It is a foundational brick of inquiry.